Okay, so thanks for the introduction. So, yeah, so this is kind of off-topic or orthogonal, but perhaps I may say in the end it's like only orthogonal on the 10 to minus 4 level, so there might be a tiny overlap to you guys. And it's spectroscopy, although I have only a dozen lines and not as many as you have. And the title is The Rise and Fall of Ultralong and Rydberg Molecules, and I will try to focus a little bit also on the fall, because this might be the connection to you here. So just to give you an idea who we are actually. So in Stuttgart, we mostly focus on frozen Rydberg gases, so we use ultra-cold gases and we excite Rydberg atoms in there. And our main focus is basically looking at interaction between Rydberg atoms. And the Rydberg molecules somehow have been a side project, so we got distracted by them, and actually we got distracted quite long, and it actually became our most popular topic because you can make like these colorful pictures, which is harder to do here. And another spin-off, like just if you just get curious, you can check our webpage. We also want to translate this ultra-cold system to hot vapors, where we want to have interacting Rydberg system in microscopic vapor cells at room temperature. But of course, I only will stick to the molecules. And this is the group, so this all happens in Tilman Pfau's group in Stuttgart, and this is a team. It's quite small. Actually, we're setting up a new experiment right now, but everything happens in only one machine, all the ultra-cold experiments. And this is a team, and we have many collaborations. So, of course, I mean, this Rydberg molecules were invented basically by Chris Green and Hossein Sadeghipour, and Zed Rittenhouse have been strongly involved in our recent papers. And also the Dresden people with Jan-Michael Rust and Thomas Pohl, and Wei-Bin Lee, who is now in Nottingham. And then, of course, in Stuttgart, we had like a strong collaboration with Hans-Peter Büchler, but more on the strongly interacting stuff. And there's one experimentalist sneaking in, so Jim actually was visiting us for a year as a, Humboldt visiting professor, and he helped us a lot because he knows molecules. We didn't know anything about molecules, we're atom people. Okay, so the whole thing is about this system. So we have a Rydberg atom, so we have the ionic core, and we have the electron. And since we have very dense samples, it might happen that one of these ground set atoms is just by chance sitting within the orbit of this Rydberg electron. And then what happens is that the electron gets bound by the core, and the scattering between the electron and the ground set atom causes an attraction which then binds basically the ground set atom to the electron, and then this whole thing together gives a bound state, which are our Rydberg molecules. And they're really huge. I mean, you're not impressed by big molecules, but still, I mean, if you compare this like to a living object like this bacteria, it's 4 times larger in dimension than this thing here. So I think it's still quite impressive to think about this in a big quantum object. To give you a little bit more insight how this binding mechanism actually works. So the electron here produces a Coulomb potential with a 1 over r squared electric field. And then you have this ground set atom, which has just an ordinary quadratic polarizability. So 1 over r squared into the electric field here gives a 1 over 2 to the r4 potential. This thing here. And now you have to do scattering theory in this potential. And actually this can be done. And the scattering theory, you can reduce this to low S-wave scattering, and then you get basically a 0 background scattering length, A0, and then you get something which is linear to the momentum, so this is the next correction, and then you get higher orders. Then you use this scattering length, which you can compute, and you use a pseudo-potential approach from Fermi, which is just collapsing everything in a scattering length time a delta function for effective interaction potential, and this is what like Bose-Einstein condensate people do all the time, and you probably know about this. But there's a funny story to this, because in this very seminal paper where Fermi basically invented this pseudo-potential, he motivated this work basically by observations of vapors, of dense vapors, where he looked at Rydberg spectra, and you've seen if you increase the density more and more, there have been line shifts in the spectra, and he tried to explain this spectrally by including some kind of pseudo-potential which disturbs the Rydberg atoms. Somehow this comes back really nicely to what we actually do, because we perturb our Rydberg atom with these ground state atoms. And the momenta, we just use a very simple classical model. So I mean, we have an S-state, so the electron moves just in a linear motion through the core, and we just take the momentum, like the energy, just as with the 1 over r potential, and we need a certain energy where it stops. So we use this momentum, we use this scattering length, and we use this one. Now we just need a mean field, like the probability density of the electrons. So we have here, for example, the 35s state. And then now we have to multiply this with the S-wave scattering length. So we have the 2pa. We have the spatial dependent velocity of the atom. So the scattering length depends on this. Then we have to take the integral over the whole thing. And so what you end up finally is a scattering, the product of the probability density times the scattering length. So this is exactly what you do in the Gross-Pitaevsky equation, for example. So we have here the probability density. We have here the velocity of the atom as a function of space. And if you multiply this, then you get kind of this potential. And you can now easily use a 1D solver, and you see immediately that you will have some kind of bound states which look kind of vibrational states. And we refer to this like the ground state and the excited state mostly, but it's not true because this is the most simple ever possible model, which even I understand. But if you do it more accurately, then you have to ask people who can do these calculations. And actually, there's one thing you have to think about. There are two things. One thing is the S-wave scattering is, of course, only a rough estimate, which only works for atoms which are far, far, far out, which are basically on the turning point. So this is this part here, and this is what I call the ground state from before, if you see here. For this very slow atoms, everything is pretty good. It seems almost to be the same potential, but if you move in, you have higher velocities, and you have to add also p-wave scattering. And then there's a resonance coming in. Here there's a p-wave resonance coming out, coming down from the next p state. And you have to include also the neighboring states at some point to really get the full potential. And what you see in the upper scale here, in the upper scale, this is like 10 gigahertz, the scale, yes? And our Rydberg atoms, the molecules, happens everything here. So if we enlarge this line by a factor of 1,000, then you see these oscillations here. And then from here, from this point, there starts a huge valley, which goes down by a factor of 1,000. So this is a deep, deep, deep hole here. And then when you have, this is basically this avoided crossing of this black line up here. And if you now compute again the bound states in here, then you can find, of course, nicely bound states here. And there's even a state below, which would be rather, we call a ground state in this outer lying region, starting from 1,000 atomic units going all the way like 2,000 atomic units. And there's a funny thing to this thing, because if you look at the green and the yellow state up there, they're actually lying above this last edge here, and they still are kind of bound in this outer well. And this is due to quantum reflection, because this is so steep here that they cannot basically penetrate this huge well out there. And it's kind of funny because I will tell you a little bit more later about the behavior or lifetime of this state and of this state. Okay, before I show you data, I have to tell you how we take the data. So we have a machine, ordinary Bose-Einstein condensate machine, which has some additional equipment. So we have some field plates inside to really apply in a controlled manner electric fields. And we have an ion detector, the electron detector. We only use the ion detector. And with these field plates, we just field ionize them after production. And the production, we use a 2-photon excitation with very narrow band laser. So we have a 5s to 5p in rubidium for the atoms. And then we go with the second photon up to the Rydberg state. And we have to detune a little bit just to hit right our Rydberg molecules. And this is just a sequence. And important thing is that we do the experiment such that we produce one ultra-cold cloud of atoms. And then we can do about several hundred experiments within one of these clouds, because it takes 1 minute to make one cloud, and if we only get one data per 1 minute, I would be still in Stuttgart. So the nice thing is that we can make 100 shots in each cloud, and at this we get an effective repetition rate of a hertz or something like this, or not of millihertz. Okay, so here's the data. Here's our experiments of what we do. So we do a photo association. So we hope that the two ground state atoms are just sitting in our favorite distance, so that we get kind of a good Frank-Camden factor. We can improve this by just increasing the density. And then we make an off-resonant 2-photon excitation. So actually we go far tuned to this 5p state that we do not actually populate it. And then we go up to the Rydberg state. And then, of course, you have seen we have like here we had bound states on the order of, let's say, 20 megahertz. So we have to go down with the laser by 20 megahertz. And then we have here a ruler, which are two atomic lines, which are split due to some offset magnetic field. We do this in a magnetic trap. And then you see here distinct resonances, which we can assign with the theory made by the full calculation. We can design this as dimer states. And there has been a little guy further out, like at like minus 45 megahertz, which actually we finally could assign to a double bound state, which is a trimer. And it's kind of, I don't know who told us that, but this is actually the first photo association of a trimer. And yes, it's just a phrase. But so we can do this, and I think if we can increase the density more, there might be even quadrimers or more. But I mean, they're physically not giving you more insight because these two guys are so far apart so that the background scattering of the ground state atoms is not giving us really new physics. So we would have to add like 100 atoms in there that we have like a 2D shell of interacting ground state atoms in there. Oh, it's far away. Okay, there are two spectra. So the upper one is the rubidium plus spectra. So this is what you expect. I mean, you have this little ground state atom sitting there. You remove the electron, so the ground state atom is freed again. And then you just detect what has been the Rydberg atom, the rubidium plus. But somehow we have been seeing also rubidium 2 plus guys. And this is kind of odd because this must be a reaction product, and we do not really understand where this is coming there, because like the two rubidium atoms form a bound state, and one electron goes away. And to give you a hint on the reaction dynamics, for example, you see these lines, which are kind of symmetric in the rubidium plus and rubidium 2 plus. But for example, like this state here, we only see in the rubidium 2 plus state, and we basically see nothing in the rubidium plus, which is a hint that this one decays immediately to a rubidium 2 plus state during the time of the experiment, and we cannot see it there. Okay, I will come back to this topic a little bit later. So we see rubidium 2 plus just by time of flight measurements, and you see that there's a square root of 2 times because it's twice as heavy when the molecules arrive, but I think you do this every day. For us, it was new. Okay, we have done this for different quantum numbers, and the theory has also been done for different quantum numbers, and then the combined results you can see here. So the black line always indicates where the molecular bound state should be, and the red lines also show you the data. And down here the dimer, and actually it fits quite well because I mean this theory, as I understood, is basically no fit parameter. They just use the theoretical scattering length A0, which has been computed quite accurately, and they put just the things all together, diagonalize the whole system to get this real potentials, and I think the agreement is actually quite good. Okay. To give you an idea how far you can go there in quantum numbers, so I have plotted here the position of this of some of the lines, and this is what I call this ground state, so the nu equals 0. This is this red state here. I mean, this is the most prominent line because it's nicely bounded here, it does not decay. And this is the trimer line, and then you see we have measured this from n equals 35 to n equals 40. And we have seen some of it at n equals 43, but not so nicely, because then if you go to 43, the binding energy already goes down to a few megahertz, and at some point you run into your atomic line, and it's really hard to distinguish these guys. On the other hand, if you go down here, then the wells is getting more and more narrow, the density has to be much higher, and it's also hard to see this Rydberg molecules for much lower quantum numbers. And actually here at this point, our experiment stops because we cannot field ionize anymore. So we have not really investigated how low you can go in the main quantum number. Okay, after this experiment, we have been quite busy in improving our laser system. So the data I've shown you are pretty much this blue data here. So we had quite a width of this line. And then we stabilized our total excitation scheme to 60 kilohertz. And then we have this new data here, the red line, and of course if you can resolve things better you might see more things. And what we have done with this new system is, I mean, we compared, we calibrate the whole thing on our atoms, and if you have a dilute sample, then you see like a line which is 60 kilohertz broad, and if you do this for the molecules, then we have actually seen lines which were much broader. in this experiment, we had to reduce because it was not so cold. It was 3 micron. We had to remove like the temperature from this, the wake potential, and then what you get is like 140 kilohertz line width for the Rydberg molecules, and certainly there is something different. And what can be the cause for this? I mean, there can be two things. Either the Rydberg molecules doesn't live so long; it just decays. So this gives a broader line if it's Lorentzian and looks pretty Lorentzian, or it's some dephasing happening in the system, which also broadens the line. It's hard to distinguish. So we needed an experiment to distinguish the real decay and the dephasing or the decoherence, and we set up a Ramsey sequence, because in this you see the both effects. You have the visibility, and I'll show you the data, so you can extract with Torres' method analytically nicely all numbers you want to have. And the thing works like this. So we have two ground state attempts. We make a first pulse. We excite some superposition of ground state attempt and Rydberg molecules. And then after time, I can make a second pulse. It comes down, and it's like pretty much the same situation as in 2002 when they produced these Feschbach molecules in ultra-cold atoms. This was like a big thing, and there has been a big article in Nature where they have like talked about coherent superposition of atoms and molecular states, and it's exactly the same thing, that they just had here magnetic field pulses, and we have light pulses, which might be useful for some future applications, but of course not so useful for pure spectroscopy. Okay, so here's our data for this Ramsey experiment. So what you see here is, if we go up in the plot from here to here, we increase the time between the two pulses, so the fringe pattern is moving together. And then you see here on the side the lobes, which are basically coming from the width of the pulses. So it's really like a double slit experiment. And then we take this data, for example, this is what we take exactly in one cloud. So we take all the whole spectra of this Ramsey interferometer with one single shot, that like one ultra-cold cloud we produce. And we fit this data to this analytical solution of the whole thing. And we get a dephasing time of 1.5 microsecond. And this is exactly what is given by the line width of our laser. So this means we do not have really additional dephasing in the system due to that the molecules does something funny, it moves around or so. And we can say, okay, everything that we see in line width has to come from some decay of this Rydberg molecule, some other states. Because the Ramsey interferometer, of course, is also sensitive if it goes to another Rydberg state. No? If it goes like from a 35, it decays to some higher L state or something like this, we will not get it back with our laser pulse. So the problem is, because we only can field analyze everything which is there, we needed some state-sensitive method to look at our molecules, and this is the method. So since we know what's going on, we can use a very simple method to measure lifetime. So we just excite our Rydberg molecules, we wait for some time, and then we field ionize, and then we see what we just get there. And as a function of TD, we see a really nice exponential decay of the data. And then if you look at the Rydberg states compared to the dimer lifetime, so the 35, 37, and of course, you have to, we have here some blackbody radiation in there. So there are neighboring Rydberg states which might not, of course, have a bound state for the molecule. One has to be careful. But the dimer lifetime here is much shorter, and actually you have to, it's about a factor of 2 what you get from blackbody radiation compared to a decay to the ground state. So still, the dimer lifetime is shorter by a factor of 2. And of trimer lifetimes are of comparable size. What I want to say, when we have taken this data, and we have been also looking a little bit on the rubidium 2+, and what we see is, first of all, the rubidium plus signal as a function of the delay time goes down, and if we look at very short times, we have basically no rubidium 2+, but the rubidium 2+ fraction is rising, so this tells us that we produce the molecules, they decay either to the ground state again, that we have a free Rydberg, that the electron is free and the ground state atom has not attached to the core, or that with the time that there's a reaction going on, that the two guys are fused together and produce rubidium 2+. we have not really data which I could show you on this because it was like just always 2 points that we have seen that it was increasing. Okay, but we might get back to this because this might be relevant perhaps to this heavy Rydbergs on the 10 to minus 4 level. As I will show in a second. Okay, so to learn more about the decay mechanisms and what might go on there, we made a more detailed study on 2 specific states. So we took one of these really nicely bound states here, which has basically no tunneling into this big well. And then we have one state which lives above this edge, or almost above this edge, which might show some tunneling. And then what we did, I mean, we have 3 channels. We have the radiative decay, which goes in there. Then we have a collision. We can change the density, and then we make a very, very simple model. We just say, like, okay, the cross-section for a ground state atom, which is still flying around there at the microkelvin temperature, might collide with this Rydberg molecule. As a cross-section, we just take the size of the Rydberg atom. And this works pretty nicely. So we have the cross-section, which is the physical size of the Rydberg atom. We have the density, and we have the velocity, n sigma v. And we have a third thing, which we call the transmission, which is basically the probability, for example, that this blue one is going into the well. And we have theoretical predictions what this rate should be. And if we look at our data, then we see if we change the ground state atom density, then we see a linear increase of the decay rate for the red one. And we see almost exactly the same slope for the blue one. So the n sigma v thing seems to fit, and there's no fit parameter in. We really take only the size of the Rydberg atom. And all other parameters are, of course, known in our system. And there's an offset from the red to the blue. And this offset, in the decay rate is exactly the theoretical value of this transmission rate. You can calculate that this thing is basically tunneling into the well. So every 1,000 times it bounces against here a few thousand times, and then it just goes into the well. So this fits nice together with the theory. One thing you might perhaps be interested about, because if you extrapolate this red curve to like 0 density, actually you do not get back your atomic lifetime. It still is a factor of 2 short compared to the atomic lifetime. So this guy also has some additional decay channels, and we have seen the rubidium-2+. I mean, this one still manages somehow to build a rubidium-2+, although it doesn't jump into the well. This one produces more rubidium-2+. It likes to jump in the well, so jumping in the well might be something which produces rubidium-2+, but actually I have no idea what's going on, since molecules are actually way too complicated for me. But you guys might perhaps have some ideas what's going on there. Okay, the last topic I want to tell, because it has been kind of a popular thing, is we are looking at the polarizability of our Rydberg molecules, and I want to compare with the polarizability of the bare Rydberg atoms. And then we have taken data like this. So what you see here is a Stark map. So we have applied electric field. So it's a quadratic Stark effect of the atoms. So this is a white line. And then you see on the left here, you see some lines which are our Rydberg molecules. And of course, it's hard to see anything in this plot. So we reduce basically the polarizability of the atom. And if we do this, then we get plots like this, where you see again our 2 atomic lines splitted by the magnetic field. And then you see here the molecular line, which actually really have a different shape. If we do this at low intensity, this is just a straight line, and this is just a straight line. But here you see we have not a straight line anymore. We have something like a butterfly-shaped thing. And if you think about this, you can see you can put in a line like this, which tells you if I increase the electric field, we get something like a linear Stark effect in this thing. And the linear Stark effect is something you would not expect from a homonuclear molecule. So we got more into details with this molecule, and we took some more data. And actually it turned out that finally we could describe the whole thing, that it's a homonuclear molecule which has a permanent dipole moment. And you can compute this dipole moment. For example, like for this data here, for the 35s state, you get something on the order of 1 dBi dipole moment, which is a really large dipole moment for this really homonuclear, almost symmetrical molecule. And I mean, dipolar molecules is a big topic in ultra-cold physics. I mean, they're producing all these heteronuclear molecules which have comparable dipole moments to this. And we do this easier. We only need one species. Okay, let me explain you a little bit more about this. I mean, first of all, the thing is that, it drops with 1 over n squared, the dipole moment. So if you go to larger Rydbergs, actually you get less dipole moment, which might be a kind of contradiction to what you think, because you think if you have higher quantum numbers, you might expect that everything is further away from the core, that you get more dipole moment, but we'll get back to this in a second. So we have done I mean, the theory people have done a full theory that calculated the real positions of the lines in electric field. So what you see here is a full calculation of the rotational states in the electric field. And how was this done? So I mean, what they have done is basically they have calculated the dipole moment as a function of the position of the ground state atom. So they take the Rydberg wave function, they take the ground state atom, put it in a certain position. This ground state atom attracts wherever it is sitting some of the wave function of the electron. It attracts it a little bit, so there's more electrons close to the ground state atom, and this excess wave function basically produces with a large distance. I mean, this is only a tiny fraction, which is attracted, like, let's say, on the 10 to minus 4 level. But since this is a really long distance, you have a tiny fraction of excess charge here, but you have a long distance, so this gives a large dipole moment. And what you have to do like this is this curve, so you have to just basically convolute this point-like function with the actual size of the wave function, then you can calculate how the real dipole moment looks like, and if you do this, then you get this 1 over n squared scaling. So since we have some finite temperature in our system, they have included in the data also some finite temperature, so this gives some blurring in the thing, and then we get this this butterfly-shaped. This is really experimental data. Where is actually this dipole moment really coming from? No? So for this, you have to look actually at this plot. So this is the wave function of this trilobite state, and if we subtract from this trilobite state just the pure atomic state, the 35s state, then you see that the wave function here has a peak far away at, let's say, at about 2,000 atomic units. You have this large peak, and this means if this is not 35s, this has to be higher L states, like P, D, and even higher L states. And what actually turns out in the end, what is important is that we really mix high L states. So the P state, of course, brings along some angular momentum, but the high L states really bring the largest amount of dipole moment. And what really counts in the end is the admixture of high L states of the manifold to the 35s wave function. This really produces then this dipole moment. And of course, you can imagine, like, if I go further out, I mean, I have a weaker, the higher the quantum number is, the more dilute is the electron function, wave function. So you get a less disturbance in the thing. So you will expect that it drops by this. But on the other hand, of course, if you go to higher quantum numbers, the more angular momentum you have, that you get larger dipole moments. So if you put this together, you have, on the one hand, you get more and more angular momentum because you go to higher numbers. But on the other hand, the thing that the wave function basically the radius scales with with n squared, that this dilution basically wins over the gain in dipole moment due to the high L states. Okay, and now, I mean, if you compare this picture, then actually it looks quite similar to this famous picture from 2000 produced by Jose and Chris Green in this trilobite state. So although it's an S state, if you look carefully, in this S state, there's somewhere hidden this trilobite state. And since this admixture is on the 10 to minus 4 state, on the 10 to minus 4 level, I say here in this context that like 10 to minus 4 of this electron wave function, like a tenth of a per mil, is attracted by the ground state atom. So it's like a 10 to minus 4, I don't know, heavy Rydberg molecule, I don't know. I mean, the position does not fit where this Coulomb potential is coming in. But perhaps I will show you now what you can do with this after. So in the conclusion, we have this ultra-long-range molecules, and we have looked at the decay mechanics, and we have looked at the at the electric field behavior, and we also have looked in the magnetic field, and we see some kind of funny stuff here, but this is like probably not so interesting for you, so I skipped this. But what you can do is like next, I mean, the first thing, I mean, you can use other elements. I mean, there are several choices for ultra-cold molecules, and Jim will talk tomorrow, I guess, or about cesium, which actually has a more interesting structure than our rubidium molecules. And there are, of course, like the experiments who have molecules already at hand, like potassium rubidium, and that would be interesting if you can basically also replace this one by potassium rubidium, and there has been a proposal by the guys here. And I'm not sure if the GLAB people are really excited about this. Probably not, but they might be doing it. And of course, I mean, you can stuff in other polarizable stuff like larger molecules, as long as the electron is not like immediately bound to this, whatever you put in there. But what can we do? I mean, we cannot just put in something like this. We don't have this in ultra cold. But there are two things which we have not looked at all in the system, which is on the one hand like dynamical effects. So one thing you might think of, I mean, if we use a state well localized here, we can generate this state. So we know that the wave function is living here. And we have pulsed lasers in our place where we can have nanosecond excitation. So you might think about like some crazy Raman scheme that you bring it up to unbound state up here. Then it's basically rolling down this hill, is shooting inwards. It might be quantum reflected here. And there are other well-localized states here. So perhaps you can use this one as a probe then later on to check where my wave function actually is. And then you dump it with a resonant laser to the 5p state. And if we do this, we make a hole here at a certain time, like we just open the trap and the wave function falls down. And then perhaps we can see by loss in the Rydberg signal where the wave function has been actually at certain times with perhaps, let's say, a few nanosecond resolution. And I mean, the energy spacings are on the 10 megahertz scale, so there's a 100 nanosecond energy time scale for moving of this wave function backhead. So it might be interesting. It's somehow imitating like this pulsed experiments with atoms where they shuffle electrons around and they do like crazy things there. And this is a crazy landscape, so this might be interesting. So this would be the radial dynamics where you might do something, but this is just a wild guess from my side. And the other thing is you also can look at azimuthal dynamics, because here, I mean, the rotational states are completely degenerate, so you cannot distinguish the different rotation states. Actually, this is an important thing that we get a permanent dipole moment, because we have like odd parity states mixing together already at this very small it's basically zero electric field, which produces a dipole moment. And of course, if we have like a rotation constant of 10 kilohertz, we cannot do anything because the molecule is just not moving on its lifetime. It's just in a certain direction and it can't go far. But if you increase the electric field, you get larger splitting between these different rotational states. And then if you get a larger splitting, then the energy, basically the energy between two states might be large enough that you really see some dynamical effect also in the rotational. In the azimuthal direction, then you can think perhaps you can generate some of these pendulum oscillations when you apply electric field. I mean, we can excite specifically here and then switch the electric field, or we can excite, I mean, there are different ways of pulsing this in arbitrary sequences and try if you can shuffle them from here to here or something like this. So it's wave packet dynamics, but actually I like this some more. Okay, and actually, yes, this is it. That's the end. Thanks.
Thank you, Robert. Questions?
I'm not sure it's a question or a comment. What you describe is actually, in my opinion, an ion pair state, but it's just the negative ion is just a scattering resonance, and then therefore you can have it at any energy you like, and it has a bit less of an electron than a real anion. But then, if you go to the limit of the real trilobite, which you presented, then if I follow your argument right, that's the exact ion pair state. So the trilobite, because it's an L mixed state, will have the electron density directly on the neutral atom per design, and then this is an ion pair state. And
if you subtract the 35s, if you subtract the 99.9% of the S state, of course.
The real trilobite, I mean, you are your spherical one. But if you go to Chris Green's real trilobite, that would, you don't need to subtract the
Picture, no? Yeah, sure, if you could go...
that's the real ion pair state.
Is it? Okay.
Or I would like to think about this as the real ion pair state.
Until 2 days ago, I didn't even know what a heavy Rydberg is, so...
Or the heavy Rydberg, I should say.
Or like a... this.
To the extent that the ion is there and the electron is over there, it's separate.
But that's what the ion pair state is.
Yes, but you still haven't done charges.
Well, you have charge separated by the virtue that you have a field. So you are charge separated, and your electron is on a neutral. So for me, that's an ion pair state, a pure one, and that's probably there's the energetic part. It's just because you're still having a scattering state, you can tune the energy that you like. So you are not going to lie precisely where the ion pair state is, because you can vary this in your collision.
Now, in rubidium, I think Phil and Ed could correct me, I think the ion pair threshold is at, just below the AP. And these are states which are...
Yes, but that's what I'm saying, because they had scattering resonance. You have no conditions on the energy that you free yourself, so you are an ion pair state that is free to be located in energy where it wants. But then, so that's the first part. And the second part, I mean, once you accept that it is an ion pair state, then you totally accept that you produce the dimer ion, because it's the reverse process as we are constantly discussing. So we discuss photoionization plus moving to the ion pair. What you discuss is ion pair going inside. Yes. And it's just the same, but you can estimate the strength of the coupling. Because you say it's 10 to the minus 4.
I mean, this is exactly the amplitude of this thing, no?
You take your rate, you multiply it by 10 to the 4, and then you get our rate for...
production of the...
Yes. Well, this is, I don't know, you can...
I have to digest it first a little bit.
Yes, on this side, I do not quite understand. Is this a triplet or a singlet state?
A triplet.
So the ion pair itself, I mean, the negative ion, has a singlet configuration. So there is a displacement, but I see how it cannot be a true ion pair, since the electron configuration is quite different.
Well, you could have an ion pair with a...
No, the electron interaction in the negative ion requires it to be a singlet.
Because it would be unbound.
Yeah, it will be unbound. There is only one bound state of the electron on the negative ion.
Because you are in a collision system, you can deal with an unbound system. That's what I'm saying.
But it wouldn't be a negative ion, an anion, an
Yeah,
anion.
it doesn't matter. It doesn't matter because it's a resonance.
Yeah, it starts to become a terminology, I guess.
It's a semantic.
Yeah.
That's why you can have it at any energy level.
Maybe Hussein could answer this, but in the picture of the trilobite, what fraction of the wave function, or what fraction of the time is the electron really sitting on the other atom versus, circulating around?
These were not time-dependent calculations.
Well, but just in terms of area, or fraction of the wave function. Because you have those two big spikes, but they're very narrow, so. What's that?
It's huge,
Which is huge?
the fraction of the time which it sits on the neutral.
I mean, you see this by the two spikes here, no? I mean, there's the largest probability.
They're very
to sit
narrow.
there.
They're very narrow, right?
Yeah, but that means the size of the atom, and it means like this is, it's a charge cloud of the electron sitting around this ground state atom, I mean.
It's a ground state.
Well, just thinking of what Frederick's talking about, if you define the size as the size of the negative ion, which is maybe 10 Bohr, something like that, what fraction of the time is the electron really
Within this
in that
10 Bohr
region?
radius to have an overlap to the
Right.
negative ion.
The real trilobite, yeah, so for your state, it's a very small fraction, 10 to the minus 4, but for the real trilobite, it has to be much bigger.
Well, that is the real trilobite.
This is a real one, I mean. This is a 10 to minus 4.
Yeah, that's exactly, so that's not 10 to the minus 4, it would be much bigger. The real trilobite.
Also, talking about the RB2 plus and possible coupling to the ion pair, in the states that you're accessing, it's really spherically symmetric, right?
The S state?
Yeah.
Yes,
There
of
we
course, but I mean, we have a really some position of the ground state atom. No? I mean, this is really localized particle at 3 microkelvin. It's not like so. I mean, it's really localized or projected on this spot.
So that other atom never really gets close, right?
Which other atom? I mean,
Oh, if-
you mean the core and the neutral?
Right.
No, it just stays there. It's frozen. I mean, it's getting close. I mean, if it makes this decay, but I mean, basically, these are time-independent states we have there. Or what is here?
I'm just wondering how it can get close enough to undergo associative ionization and produce the RB2+.
I can go by tunneling into the well. No? I mean, this was the steady-state potential, but then basically you can make some dynamical guess where it's like basically bouncing against this well, and every 1,000 times it's going down the well, and the bouncing time is given by the width basically of this bound states. Jimmy is not happy? No? Okay.
When it penetrates into so the wave function is piled up at long range, but then as it penetrates into the part where the potential actually plunges down, then it can, I mean, that's where this stuff happens.
So my picture is like, I mean, you have like all these bound states there, which like have a depth of 20 megahertz. So the time scale for like say one turning for one traveling back and forth on the order of 50 nanoseconds. So every 50 nanoseconds it knocks on the door if it can go to the well, and every 1,000 times it goes actually there, no? Or every 100th times.
And in this picture, does the rubidium sort of leave the electron behind at the
This is, I don't know, but this I
does it drag it along in the motion?
because this
sort
is-
of connects it against the
I mean-
picture that Frederick.
I mean, this is then a dynamical thing where I'm not so sure what the Born-Oppenheimer thing is doing there, because if we go down the well, I mean, there's a complete different energy scale, and then I have no idea if the wave function, I mean, what we have here is a Born-Oppenheimer picture, no? So if you do a very rapid process, and the electron, I think, I don't know, but I imagine that this is much more complicated, no?
I think it's unknown.
Any other questions for Robert, or shall we stop lunch? Maybe we should stop. So we now have